Okay, so Newton's third law. The big thing with Newton's third law we talked about yesterday is that mathematically it always breaks down to a Newton's second law question. Sum of all forces, m times a, that kind of stuff, right? And it's usually a system because it usually involves more than one mass. Because, well, it has to. If you're exerting a force on something, it has to exert a force back on something, so we're always going to have that action-reaction pair. So we've got here these two logs, okay, so log A and log B. Okay, log B, is 250 kilograms, and it's attached by a chain to log A, which is smaller, has only 150 kilograms. Wow, I'm struggling with my writing today. Okay, and every day. That's not something new. Then it's being pulled by a team of horses using 2,600 newtons worth of force. Okay. The next thing they tell us in part A is that the horses, not only do they pull with 2,600 newtons, but the force of friction on the whole system is 2,400 newtons. So I can simplify this down to a 400 kilogram mass being pulled this way by 2,600 newtons and this way by 2,400 newtons, which means my net force is 200 newtons. Have I done anything Newton's third law related yet? This is all Newton's second law right now. Okay. So I've got an F net of 200 newtons. I want to find the acceleration, so that's just going to be F net divided by m. 200 over 400 is 0.5 meters per second squared forward. Okay, so I've done part A. Part A involved no Newton's third law information or work at all. Okay. In part B, it says that the force of friction on log A is 900 newtons. Calculate the force exerted by log B on log A. All right, so now I can't treat this as one 400 kilogram system. Now I've got to look at it in separate parts, a 150 kilogram log, a 250 kilogram log, and I got to look at the forces individually. Okay, so what do you suppose is my best bet for starting this? Log A or log B?
Log A.
Log A is easier. There's one less step. It's not that log B is difficult, but there's one more step. It's subtraction. It's not overly difficult, but it's still an extra step. Okay, so I'm going to start with log A. 150 kilograms. Okay, it's being pulled forwards by 2,600 newtons worth of force from the horses because the horses are directly attached to it. What forces are acting back on it? Friction. And they told me that that is only 900 newtons. Any other forces acting back on it?
Log B.
Log B. Yeah, that's the Newton's third law part of this. Okay, if it's going to pull on log B, which it is because it's connected to it by a chain, log B has to pull backwards on it. Okay, that's the Newton's third law action-reaction part. So we've got the force of B on A, and that is what they are wanting us to calculate. Okay, they're actually wanting us to calculate the force of A on B, but that's okay because they're equal but opposite in direction. Okay, so what do I need to calculate next? Net force. Yeah. I've got to calculate net force. I know the mass, I know the acceleration, so I can calculate the net force acting on log A. All right, so F net equals 150 kilograms times 0.5, so that's 75 newtons forward. All right, I now know what those three forces add up to, and I know 2 out of the 3 forces. Can I find the one I'm missing? All right, so we're going to say then that F net, so this is the sum of all forces part. We've got force of the horses, okay? We've got the force of B on A, and we've got the force of friction. All right, so we're looking for the force of B on A is going to equal net force minus the other 2. So minus the force of the horses, minus the force of friction. But I have to keep my vectors in mind here. 2,600 newtons forward. Okay, sorry, that's the force of the horses. 75 newtons forward, minus 2,600 newtons forward, minus 900 newtons backwards. Okay, that one needs to be negative. When I do this, I get 1625 newtons, but we only have 3 significant figures, so that'll be 1.6, 3 times 10 to the 3 newtons. The force I calculated, that's forwards. The force they want, it's backwards. Okay, so Newton's third law comes into this problem for a grand total of about 10 seconds. Okay, once in the middle there to figure that force out, and once at the end to remember I got to switch the sign to the other way. Okay, and that's it. All right, how are we feeling about the Newton's third law stuff? Yeah? Okay for that? So on your exam, I'm going to ask you one like the 2 boxes. Okay, like I showed you yesterday when we did kind of near the end of class. Okay, but there are easier ones. Could end up maybe in a multiple choice question. So there's a few questions in the digital workbook that I'd like you to try that are on Newton's third law. And then we're going to do a little quick kind of fun activity on what happened if everybody jumped. And then you'll love it. Okay. So yeah, let's have the digital workbook open, and we're working on the Newton's third law problems. I think they're on like page 6. Is that right? Is that page 6? Page 5. Okay, so there's 4 Newton's third law problems, and they're all way easier than the ones we did. They're basically just 2 people push off of each other. Okay, so they're super easy. Okay. Give them a try, and then we can go through any that give us trouble. Okay, so on number 4, okay, we've got a student whose mass is 45 kilograms. So we're just going to say mass of the student. Okay, 45 kilograms. Mass of the object, okay, is 3 kilograms. And they're throwing the ball to her right. Okay, so they're going to be exerting a force on the ball that is to the right. Okay. During the throw, the object was accelerated horizontally through a distance of 0.6 meters. Okay, from rest to a velocity of 9.6 meters per second. Okay, calculate the velocity of the student when the object was released. Okay, so the initial velocity of the student is also going to be what? 0. Okay, she wasn't running when she threw it. At least it doesn't say that, so I have to assume she wasn't. Okay, so what I'm going to do first is I have to obviously recognize that the force on the student and the force on the ball are equal but opposite in direction. And I have enough information right now to calculate the acceleration of the ball. With the acceleration of the ball or object, whatever it is, I can calculate the force on the object. That will be the force on the person, on the student. And then I can go from there. If I know the force on the student and their mass, I can calculate the acceleration of the student, and from there I can calculate the velocity of the student. I will likely have to calculate the time, because I don't have the distance the student moved during the acceleration. I have the distance the ball or the object moved, but not the distance the student moved, and they would be different because of their different masses. Okay, so I have to keep that part in mind. So first thing I'm going to do is calculate the acceleration of the object. I'm going to use VF squared equals VI squared plus 2AD to do that, but I'm going to manipulate it for A. So VF squared minus VI squared over 2D. Okay, so that's going to be 9.6 squared minus 0 divided by 2 times 0.6. Okay, so I've got 9.6 squared, okay, and I'm going to divide that by 2 times 0.6, which is going to be 1.2. All right, so I'm getting an acceleration here of 76.8 meters per second squared. that's a lot. But when you're considering you're throwing something, it's not unreasonable. Okay? It's about 7 Gs. It's not unusual. A roller coaster you would experience between 3 and 5 Gs. Okay, things like that. So it's not unreasonable to expect that you could accelerate something that quickly, at least over the short period. Okay, so now that I know the acceleration of the object, I'm going to calculate the force on the object. And I'm going to take the object's mass, 3, and multiply it by the acceleration, 76.8. Okay, so there's the force on the object, 230.4 newtons. All right, so the force on the student is negative 230.4 newtons, or 230.4 newtons to the left. Okay, so now I want to look at just the student's information. So I'm going to kind of get rid of all this here and say, all right, mass of the student is still 45 kilograms. The initial velocity of the student is 0 meters per second, okay? And the force on the student is 230.4. So I want to calculate the acceleration of the student. 230.4 negative divided by the mass of the student, 45. Okay, so they're going to accelerate at 5.12 meters per second. Now I know that seems like a lot. But again, it's for a short period of time, and they're standing on a frictionless surface. Imagine how hard it would be to throw something if you couldn't plant your feet. Okay? You would definitely fall, okay, if you tried to do this, and that would count as an acceleration. Okay? So 5.12 meters per second squared, and we'll say that's to the left. Okay, so I've got acceleration, 5.12 meters per second squared. Okay, I don't have enough information with that to calculate VF. I need one more piece of information, and I have to use the object's information to get it. What's the only thing that the person and the object have in common during all of this besides force? Time. The acceleration will take the same amount of time for both. It will last as long as they're in contact with each other. So I'm going to go back to the object information where I've got VF, VI, and D, and I also have A because I've calculated it, and I'm going to calculate the time. I'm just going to go time equals VF minus VI over the acceleration that I calculated. So that'll be 9.6 minus 0 divided by 76.8. All right, so this is going to take 0.125 seconds. That's reasonable. It doesn't take you long to throw something. Okay, so 0.125 seconds. That I'm going to bring down here. All right, can I now calculate the final speed of the student? So I'm going to say VF equals VI plus A times T. Since VI is 0, it's just A times T. So 5.12 times 0.125 should give me, okay, my 0.64 meters per second to the left. Okay, it's tricky, that one. That's why it was the last one. I would never ask you one like that on a test. It's integrating a lot of things. Maybe on a final exam where I want to integrate a lot of things onto one question to make the test shorter, but not on your unit. Not on your final exam. Okay, does that make sense? It's just a lot of like nitpicky kind of work on a question like that. All right, I want to go through this activity that examines what would happen if everybody jumped. Okay, because we looked at the ridiculous Nike ad yesterday, where if everybody ran, they could reverse the spin of the earth, which is stupid. Okay, but now we're going to look at what would happen if everybody jumped. It would be very bad. Very, very bad. Okay? So, at the start of this scenario, the entire Earth's population has been magically transported together into one place. Because how else would you get 6.5 billion people all into one place, or 7 billion people all into one place? The only way you can do that is by magic. So we did it. It's magic. Everybody's in one place. Okay? A crowd that size takes up an area the size of Rhode Island. okay, which is the smallest state in the United States. But there's no reason to use a vague phrase like an area the size of Rhode Island. We're just going to say everybody's in Rhode Island. Okay? So the entire state is covered in people, which for someone like me would cause enough anxiety to probably have a heart attack.
Is that just like shoulder to shoulder?
Shoulder to shoulder, packed in like sardines. Anyone else feeling anxious about this situation? Especially in COVID. We wouldn't want this. Okay? So, that's what we've done. At the stroke of noon, everyone jumps. Now imagine coordinating this. Just think about the coordination involved in getting 7 billion people to do what you want all at the same time. I can't get my 2 kids to do what I want, not at the same time. Okay? Never mind 7 billion people. So, as discussed elsewhere, it doesn't really affect the planet. Earth outweighs us by a factor of over 10 trillion. If you recall yesterday, I wrote the mass of the Earth on the board, 5.98 times 10 to the 24 kilograms. Okay, that's a really big number. Okay, on average, we humans can vertically jump maybe half a meter on a good day. Okay, some people are really athletic and they can jump higher than that. Some people are like me and their athleticism left them long ago and have a credit card vertical. Okay.
What about the old people and the sick people who are bedridden?
Oh, exactly. Like this, the whole thing just falls apart, right? There's all kinds of holes we can poke in it. Babies can't jump. Is mothers going to hold the babies and jump at the same time? Yeah. How do you get everybody to jump, right? It's all magic. It's the only way. Okay. So everybody jumps. Okay. So on average, about a half a meter on a good day. Even if the Earth were rigid. That is absolutely so you couldn't like even make footprints in it, okay? And responded instantly, it would be pushed down by less than an atom's width. Okay, so very, very small. Next, everyone falls back to the ground. So that's just the forced jump. Then there's everyone coming back, okay? So technically, this delivers a lot of energy into the Earth. I mean, it is, after all, a lot of people. And when they get to a certain height, they have a lot of potential energy. When they fall back down, they have a lot of kinetic energy. Okay? And when they hit the Earth, that kinetic energy does work on the Earth. Okay? But it's spread out over a large enough area that it doesn't do much more than leave footprints in a lot of gardens. A slight pulse of pressure spreads through the North American continental crust and dissipates with little effect. The sound of all those feet hitting the ground creates a loud, drawn-out roar which lasts many seconds. Eventually the air grows quiet. Seconds pass. Everyone looks around. Why did we do that? People start questioning their motives. Okay? There are a lot of uncomfortable glances. Someone coughs. That would be really bad. Then, people would freak out. Okay? A cell phone comes out of a pocket, and within seconds, the rest of the world's 5 billion phones follow. All of them. Even those compatible with the region's towers are displaying some version of no signal. The cell networks have all collapsed under the unprecedented load. Okay. Outside of Rhode Island, abandoned machinery begins grinding to a halt. Remember, everyone's in Rhode Island. If you live in France, that's scary because most of their electricity is generated by nuclear power and nobody's supervising the plant. Okay, nobody's supervising anything right now because they all just jumped for some reason in Rhode Island. Okay, so outside Rhode Island, yeah, it all grinds to a halt. The T.F. Green Airport in Warwick, Rhode Island handles a few thousand passengers a day. It's kind of like the Fort McMurray Regional Airport. Assuming they got things organized, including sending out scouting missions to retrieve fuel, they could run at 500% capacity for years without making a dent in the crowd. Because apparently we can only magically transport everyone there. We can't magically transport them all home. This is going to become a problem. Okay. In addition, all of the nearby airports, the addition of all the nearby airports doesn't change the equation much, nor does the region's light rail system. Crowds climb on board container ships in the deepwater port of Providence, but stocking sufficient food and water for a long sea voyage proves a challenge. Rhode Island's 500,000 cars are commandeered. Moments later, I-95, I-195, and I-295 become the sites of the largest traffic jam in the history of the planet, something like the first season of The Walking Dead. Okay? just roads with cars jammed everywhere, okay? Most of the cars are engulfed by the crowds, but a lucky few get out and begin wandering the abandoned road network. And some make it past New York or Boston before running out of fuel. Since the electricity is probably not on at this point, because no one's supervising the plants, okay, rather than finding a working gas pump, it's easier to just abandon the car and steal a new one. You see society breaking down here to lawlessness? This is what would happen. Okay, who can stop you? All the cops just jumped there in Rhode Island, so yeah. Okay, at the edge of the crowd spreads outward into southern Massachusetts and Connecticut. Any two people who meet are unlikely to have a language in common. Almost nobody knows the area. The state becomes a patchwork chaos of coalescing and collapsing social hierarchies. Walking Dead. Okay, yeah. Okay. Everybody is hungry and thirsty. Grocery stores are emptied. Fresh water is hard to come by, and there's no efficient system for distributing it. Never mind the sewage. No one's mentioning that. Okay. Within weeks, Rhode Island is a graveyard of billions. This didn't work out well. Earth's fine. We're not, because, yeah, we all jumped. Okay. Survivors spread out across the face of the world and struggle to build a new civilization atop the pristine ruins of the old. Our species staggers on, but our population has been greatly reduced. Earth's orbit is completely unaffected. It spins along exactly as it did before our species-wide jump.
Natural selection.
Well, yeah, maybe something like that. Okay. All right, so let's look at this from a mathematical perspective, or from a logical perspective. What are some problems with synchronizing everybody's jump? Can you see from one side of Rhode Island to the other? How long would it take sound to travel that far? A long time. It's not like I can have a starter's pistol and just go bang and have everybody jump. That doesn't even work here. Okay? If someone starts the 200 meter at one corner of the track, the people at the timing gate at the finish line have to watch for the smoke, because if they start the watches on the sound of the gun, they're going to be off by a whole second. Okay? So that's not going to work. The jump won't be coordinated by sound. Okay? And we already know we can't use cell phones to signal everybody. Okay? Even when they do an emergency alert, we don't all get it at exactly the same instant. Okay? You guys have had that happen. Okay, so we don't get it at all exactly the same instant, and it would already make the cell phone network crash anyway. So that's not going to work. How do you get this? Not everybody's watch is set to the same time, so you can't say at the stroke of noon, everybody jump. Oh, I missed it, right? Like, it would be almost impossible. Okay, give everybody what?
A watch.
Give everybody a watch, and not even everybody has a watch, but even if you give them all a watch, you're not going to set it all the same, right? In here, our watches are probably all different by a few seconds, okay, for sure. All right, calculate the total mass of the Earth's population, assuming the average mass is 65 kilograms. Okay, we're going to make that assumption. There's going to be a lot of people that are lighter than that. There's going to be a lot of people that are heavier than that. We're just going to say that's the average. Okay, so Earth's 7 billion people. So 7 billion. That's 700. That's 7 million. 700. That's 7 billion. Okay, 7 billion times 65. Okay, so there's the mass of the entire human population of Earth. 4.55 times 10 to the 11 kilograms, which is a lot different than 10 to the 24 kilograms. Okay, so a lot lighter. All right, we got that number, 4.55 times 10 to the 11. Okay, calculate the maximum gravitational potential energy of the crowd when they are at the maximum height of their jump. Anybody remember from Science 10 how we calculate gravitational potential energy? Oh, those of you who are in my Science 10 class should know that. Okay. That formula, M times G, now everybody knows their head, yeah, sure. Okay, so we got our mass, that big number, okay, times 9.81 times the height everybody jumped. We said on average that's half a meter. We're just going to simplify and say everybody jumped a half a meter. I'd love to be able to jump half a meter again. Okay, I'm old. So, that's the one. Okay, we're going to take that number and multiply by 9.81 by 0.5. Okay, so there's the amount of energy possessed by the crowd when they're at the top of their jump. It's a lot. Okay, for sure. Okay, determine the kinetic energy of the crowd as they strike the earth. Remember the law of conservation of energy? If they have that much potential energy, how much kinetic energy do they have when they hit the ground? Same amount. Okay, so we've already done that. Okay, determine the maximum kinetic energy of the earth as a result of the crowd hitting it. Would it also be that number?
Yeah.
Assuming everything was perfect and the earth was a rigid ball, yes. Okay, and we're going to make that assumption. All right, calculate the maximum speed of the earth as a result of the crowd hitting it. Okay, since none of you remembered what the formula for potential was, I'm going to assume no one remembers the formula for kinetic. Okay, 1/2 mv squared. I know the mass of the earth, 5.98 times 10 to the 24. I know the energy, okay, because I calculated it's on my calculator. Can I calculate V? Okay, so V is going to be the square root of, okay, EK divided by 1/2 of m. So I'm going to take that number I calculated, that's the energy, and I'm going to go square root of, oops, that number divided by 0.5 times 5.98 times 10 to the 24. Whoops. (8.6 times 10 to the -7 meters per second. So like 0.000000086 meters per second squared. Did we knock the Earth out of orbit?
A little bit.
Okay, just so you know, the Earth's orbit's not a perfect circle. It changes by like 5,000 or 6,000 kilometers at any one point in its orbit. We did nothing, okay? Absolutely nothing, right? So there are times in the Earth's orbit where it's 5,000 kilometers closer to the sun than at other points.
I feel like saying that we did nothing would be wrong, because if so many billions of people died, global warming would definitely slow down.
Oh yeah, yeah.
So,
So we did nothing to the Earth's orbit.
yeah,
Is that better?
yeah.
We killed human civilization, but we did nothing to the Earth's orbit. So yeah, you're right. We absolutely did accomplish something bad. Well, it depends on your perspective. Emmanuel might make an argument here.
Well, since Earth's in space, wouldn't it keep moving very, 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 very slowly?
Well, if there were no other forces involved, yes, but you've got gravitational pull from the sun, from the moon, all that kind of stuff like that. That's not going to do anything, right?
And it's not a rigid body.
And it's not a rigid body, exactly. Yeah, we're going to compress the soil a little bit, and that would be about it. Okay, so there you go. If you were wondering, there's the math behind why that Nike ad was so dumb. Because it's exactly the same for everybody running the same direction. Okay? It will cause absolutely nothing to happen. All right. Everybody good with that?
Another reason that that was done was for the Earth to stop, it would need to decelerate really quickly.
Yes.
And that would kill everybody.
Yeah, everyone would be thrown to one side of the Earth. Yeah. Yeah. The whole idea that the Earth would just stop for some reason is ridiculous. Like, again, it's like magically transporting everybody to one place.
There's another what if article about what if the Earth stopped.
Yeah, you were telling me about that. Yeah, if the Earth stopped rotating. Yeah, I mean, if the Earth stopped rotating, yeah, there'd be a lot of things that would go very, very wrong. Okay. Basically, everybody would have to live along the Terminator, which sounds really cool, but is very bad. Okay, because we'd all have to live along where day and night meet. Okay? Because if we lived on the night side, we'd freeze to death. If we lived on the warm side, everybody would cook. But in addition to that, the Earth has an atmosphere, and if you've got a difference in temperature between one side of the Earth and the other, okay, wind, exactly. There would be gale force winds basically all the time, trying to equalize temperature and pressure between the two sides of the Earth. Okay, that Earth would become very inhospitable very, very quickly. were that to happen. Right? Plus, you'd never have sunrise or sunset again unless you lived at the Terminator where you could have it all the time.
It'd be a nice sight.
What's that?
It'd be a nice sight
Yeah, I guess.
before you die.
Yeah. Be really weird. Definitely. Okay, so that's all we need to know about that stuff. All right, I'm going to give you guys about a 5-minute break here, and then we're going to start talking about work energy theorem. So that'll be kind of review. Work energy theorem is without a doubt the most important concept in high school physics. Okay, I do not exaggerate when I say that. It is going to be part of a lot of things in physics 30. Okay? Because without work, there can be no change in energy and nothing can happen. And you have to have energy to do work. It's a vicious cycle. Okay? It's not a chicken and the egg argument though. Okay? Everybody always says that. What came first, the chicken or the egg? Eggs. Eggs came before chickens. Chickens are birds. Birds evolved from reptiles. Reptiles lay eggs. Eggs before chickens. Argument over. I don't know why people ask that. It's the same as when people go, when a tree falls in the forest, does anyone hear it? Doesn't matter, it makes a sound. Okay? If there's no one there, obviously no one hears it. But it always makes a sound. All these philosophical things just don't make any sense to me because I have logical answers for all of them. Okay, so we got to understand what work is very simply, okay? And also very importantly, work is a change in energy, in mechanical energy in particular. If I do work, I change the mechanical energy of either an object or a system. Okay? So if I pick something up off the floor and put it on a desk, have I done work? Yes, because I've changed the mechanical energy of that object. I've taken it from the floor, where it was stationary and couldn't fall any further, and put it on a desk, where it's still stationary, but could fall. It now has gravitational potential energy, and the only reason it has it is because I gave it to it by doing work. Okay, do you want to follow me on that? Okay, it's the same as if you set a mousetrap. Okay, so if you're setting a mousetrap, you pull the killing bar back, and that, it's actually called that, by the way. Okay, you pull it back, and that changes the shape of a spring. Okay, you have to exert a force through a distance in order to compress that spring. Okay, when the mousetrap has already been triggered, it has no energy because it no longer has any potential energy and can't do any work. But when I reload it, I do work. I put potential energy into the spring, and now the spring can do work again. Okay, so all of that involves changing the mechanical energy, whether it's potential energy or kinetic energy, doesn't matter. Any part of mechanical energy is changed, I've done work. Okay? So, what's the relationship between force and work? Well, this one. You learned this in Science 10. Work is force times distance. The more force I exert, the more work I do. Okay? If I exert that force over a greater distance, the more work I do. And learn that depending on the situation, work and energy can be equal. So in the example, if I pick something up and put it up on the desk, if I do 200 joules worth of work in doing that, how much energy does the object have? 200 joules. It's law of conservation of energy, right? I did that much work, that's how much energy it has. In the perfect physical world, of course. Okay, so strictly speaking, work is done if a force is exerted through a distance. Okay? Because that's the only way I can change the mechanical energy of something. I either have to change its shape, change its height, or change its speed. Any change in those things means I've done work. I've exerted a force through a distance to cause that. Okay? All right, so this person here, they've got a stalled car and they start pushing it. Okay, so if it starts from rest and then he gets it rolling, what type of energy has he changed about the car? He's changed its velocity, which is related to what kind of energy? Kinetic energy. Okay, remember, the types of energy we deal with are gravitational potential energy, which is affected by mass, acceleration due to gravity, and height, and kinetic energy, okay, which is 1/2 mv squared. So it's affected by speed and mass. Okay. In Unit 4, we'll also look at elastic potential energy. Okay, which has to do with the type of energy in any elastic object. Right? If you change the shape of an elastic object, you give it elastic potential energy. So when you stretch a rubber band, okay, you exert a force through a distance, you put elastic potential energy in the rubber band. If you compress a spring or stretch a spring, same thing. You've exerted a force through a distance, there's now elastic potential energy in the spring. Okay? No, we don't deal with that in this unit, we deal with it actually in the last unit. Okay, so for this unit, we're just going to be concerned with gravitational potential and kinetic energy. Pushing a car means I exert a force on the car over a distance, which changes its velocity, which changes its kinetic energy. Okay, everybody all right with that? Okay, so the units for work are a Newton meter, okay, which we abbreviate joule. Right? The reason we get that, work is force times distance. The units for force are newtons. The units for distance, meters, Newton meters. You never have to write it as Newton meters, just write it as joules, J. Okay? Now, these girls, they're pushing on this rock. It doesn't look like they're pushing very hard, but they really are. The rock doesn't move. Have they done any work? They've done work. Have they done any work on the rock? No. Okay? They've done work because they're expending energy.
It's really freaking me out.
Okay. So they haven't done any work on the rock because they haven't changed the mechanical energy of the rock. They have, however, changed like the thermal energy of the area by exerting a force, okay, on the rock that has resulted in them expending energy. So there's work being done if I push on something and it doesn't move. But the work being done is actually on me. So if I push on the wall like I did yesterday, I'm going to be really gentle because it's cracking still. Okay? So if I push on the wall really, really hard, the wall, I mean, it moves because it cracks, but okay, it's not moving very far. I'm certainly not changing its energy, right? But I'll get tired if I keep pushing on the wall. Why? I'm not transferring any energy to the wall. I'm not changing its mechanical energy. But when I push on the wall, what does the wall do? It pushes back. What happens to my muscles when I use them? They get tense. I'm thinking of a word that starts with C. Does that make them shorter? Is that a change in distance? Force times distance. Okay, the work comes back to me. I have to brace myself against the force of the wall. Okay, in doing so, I expend energy. It doesn't end up being mechanical energy. It ends up being sound, me grunting and groaning, okay, and heat and thermal energy and stuff like that. Okay, but it's still there. It's still accounted for. Okay, that just explains why you get tired, even if you accomplish nothing mechanical. Okay, you still get tired, and that's why. Okay, now, in Science 10, when we dealt with force times distance, it was all the same direction. I pulled something forward, it went forward. But in this course, we've dealt with situations where I pull something at an angle, but it goes forward, right? And is all the force I'm exerting, like in this situation here, all the force that's being exerted in the handle, is all of it doing work? No, because the luggage isn't going that way. The luggage is going this way. the work being done is in that direction. Okay? Or the energy that's being changed is only happening horizontally. So I have to take into account that only a horizontal component of that force is actually causing the change in energy. Okay? Since I'm not moving the luggage carrier vertically, I'm not changing its potential energy. I would just be changing its kinetic energy. Okay? Provided I made it go faster. It's really starting to freak me out. Okay, at least it went away that time. So, what if I roll this thing at a constant velocity? What if I don't accelerate it? Do I still do work? Yes. Against the force of friction, exactly. Okay, I still have to overcome the force of friction. I'm still going to be exerting a force through a distance. It's just instead of changing the mechanical energy of the cart, I'm going to be changing the overall energy of the surroundings. I'll be adding sound and thermal energy, heat, okay, things like that. I'm still going to be losing energy in this process. That counts as work. It's just not mechanical work that's actually going into the luggage carrier. Its energy isn't changing if I pull it at a constant velocity. Okay? Everybody all right with that idea? Okay, so if I've got an angled force and I want to calculate how much work is done, in this case it would be against the force of friction, okay, by pulling at 75 meters, I would use still this. Work is force times distance, but I'd use cos of theta to get the part of that force that is actually acting in the direction that the box is going. Okay, everybody all right with that? If the force and the work are in the same direction, what's theta? Zero. What's the cos of theta? What's the cos of 0? Sorry. 1. Okay, that's why it works. You can put f cos of theta in there, and if they're parallel, if they're in the same direction. If they're in the same direction, then theta will be 0, and the cos of theta will be 1. So you're going force times 1, which doesn't change it, times distance. Okay? All right, so if we did that in this case, we'd be doing 2,170 joules worth of work in pulling that luggage carrier 75 meters. Okay? So you're burning some calories pulling your luggage around the airport. Okay, what about this situation? So I'm bench pressing. The weight of the barbell is 710 newtons. Okay, that means if I want to move it, I have to exert how much force? Well, actually 710 newtons. I can make it move at a constant velocity if I exert exactly the same force as its weight. Okay. So I exert 710 newtons worth of force up. Okay, have I changed the energy of the barbell? I have. I haven't changed its kinetic energy, but I've changed its, yeah, it has the ability to do work now. Okay, if I let it go, it's going to do work on me, and it's going to change my shape in an undesirable way. All right, so it definitely has energy because I gave it to it. I pushed it up into the air, and now I'm holding it there. All right, now, what happens when I lower it?
Changing distance.
Okay, but I lower it the same distance, right? Like it just comes back down here. Well, where does it go? Yeah, it does. Okay, it comes back to me. I have to work either way. Okay, and I see people who do this wrong at the gym. Okay, there's like people are like they're pushing and they've got this massive amount of weight and they get it up and they're like yeah, and then they just like poof and they just let the thing come crashing down. Okay, onto the rack. Okay, it's like well, you only did half the workout then. Okay? If you work out properly with weights, you work just as hard to lift them as you do to lower them. Okay? You get much more benefit out of your workout if you're doing it that way. But I see people that, they're doing dumbbell curls and and they let it drop. Okay, like you're not getting anything out of the second part of that motion. If you lower it just as slowly, you're exerting just as much force to lower it as you did to raise it, and you get twice the benefit out of the workout. Okay, so in that case, then the work that's done to the barbell gives it energy, but when I lower it back down, it has to lose that energy. Okay, so the work going up is positive. The work going down is negative. All right, so when this goes up, the force I'm exerting is in the same direction as the work. So theta is what number? 0. When I lower it, I'm exerting a force upwards. Which way is the barbell moving? Down. What's that angle? (90) would be at a right angle. 180. What's the cos of 180? -1. Okay, so when I go force times the cos of 180, I get a negative number because it's giving all that work back. Okay, it's losing the energy as I lower it. Okay, it no longer has the ability to do work once it's back down and on the rack. Okay, is that sort of making sense? Now, I just got through saying all this stuff about work being like positive or negative, but work's scalar. We'll talk about that little chestnut on Friday, because tomorrow we're doing a lab on friction. Okay? All right.